Hi everyone, welcome to my latest video. Today I'm going to be discussing the creation of a single application Linux. My name is Michael Mullen and let's get started. So the agenda for today is that I'm going to talk about what a single application Linux is, why you would want to make one, why you would not want to make one. Then I'll go through the components of a single application Linux, and then I'll give a demo. So what is a single application Linux? Well, to simply put, it's a Linux distribution that only runs one single application. So why would you want to make one of these? Well, it's an extreme case of the Unix philosophy, do one thing and do it well. So what you can do with a single application Linux is that the application that you are running can use all of the CPU, it can use all of the RAM and all of the hard drive. Of course, it has to share with the kernel, but it doesn't have to share with other user space programs. It doesn't have to share with systemd or print servers or logging or anything like that. It can use up all of the machine that you want, all of the machine that you have. Other reasons to do single application Linux is that you have a much smaller security footprint because an attacker can't compromise processes that just don't exist. So recently there's been a problem with a new security vulnerability found in sudo. Well, you can't compromise sudo if sudo doesn't exist on the machine. And then the last reason to do a single application Linux is to learn the fundamentals of Linux at a really base level. And what you can do with a single application Linux is you can get all of the other applications, the other daemons out of your way so that you can learn kind of from the ground up. And let me show you what I mean. Let me show you what I mean by this. So in the demo here, I have an application that that runs a web server, and I'm in the demo. I'll show you running it on the single application Linux, but I'm going to just show you the application running on my Fedora machine right now. So let me build up the application, and we should probably zoom in here so you can see what's going on. And now I am going to run that application. So it's up and running. And what it does is not important right now. What I want to show you is what's going on with that application. So that application is called sal_app. So here is a list of all the processes on my machine running right now. And if we find sal_app, you will see that sal app is a child of bash, and bash is a child of gnome terminal. Gnome terminal is a child of systemd-user, which is a child of systemd, which is switched root from the initramfs starting up. So you can see that just to reason about this sal app, to get a full understanding of this sal app, you have to understand that it was run through bash, which is run through gnome terminal, which is run through systemd, which is run through systemd, which is not a child, but the first process that the Linux kernel runs. So that's a whole lot of things to kind of learn about if you want to learn the fundamentals. So let me clear this out. Let me quit the application here and get back to the presentation. So what I'm trying to say here is that it's easier to explore Linux on a fundamental level if you're only running one application. Of course, you don't have the tools to explore Linux, but you can add a single application Linux into your repertoire of learning. So here's some things that you can do with a single application Linux. say you've got a number crunching problem. You are trying to find millions and millions of SHA 256 hashes, and you want to do this as fast as possible. So you want to devote all of your machine to this one application, and you don't want to worry about your resources of your machine being stolen by daemons or by logging or by anything like that. Well, you can create a single application Linux to do that. Another thing that you could do is something that you might normally do on a microcontroller, but you want a little bit more out of what a microcontroller can give you. For example, so you want the ease of hardware enablement that the kernel can give you. So you've got a little Linux stick, and the Linux stick has USB ports, and you can plug in these USB ports, and your device, which is running the single application Linux, can understand these USB devices because the kernel does all of that USB work for you. And this kind of leads into Raspberry Pi products. So you've got a Raspberry Pi, and Raspberry Pis traditionally haven't been very powerful. And one of the reasons why they're not very powerful is because they're running a whole bunch of different things. But one of these Raspberry Pis is many times more powerful than my first computer was. So there's no reason why these Raspberry Pis can't run a single application very, very well. So there's a bunch of reasons why you would want to do this. But why would you not want to do a single application Linux? Well, if you're trying to solve a complex problems on a single application Linux would require you to reinvent a lot of wheels. So Isaac Newton said, "If I've seen further than others, it is because I'm standing on the shoulders of giants." And what that means in a technological sense or in a Linux sense is that if you're doing a single application Linux and you want to have a graphical user interface, well, you're going to have to build all of that graphical user interface to do things, and that's a lot of work. Or if you're running a security application, you've got to reinvent all of these security patterns. And in my demo, I'm going to show you that you're going to have to re-implement all of the security settings to do work that you want done. And because other people have done all this stuff for you, it doesn't make sense to redo it. Another thing is that even if you do reinvent all of these things, your reinventions will probably be worse than the inventions of those who came before you. And that's because all of these other projects have been battle tested. And now they may still contain bugs, but they also contain the source code for thousands of previously found bugs that have happened in the past. So I was recently reading an article or a forum post about someone who is thinking about redoing sudo in Rust. And Rust is the perfect programming language to do sudo. The recent vulnerability in sudo was because of a memory allocation problem. And Rust just doesn't have those problems. So it's a really good idea to write sudo in Rust. The problem is that sudo, this one vulnerability is just one of thousands of previously found bugs in the sudo application. So if you are going to reinvent sudo in Rust, you might solve this memory allocation problem, but you're going to run into all of the other bugs that have previously been solved. And then the other reason why you don't want to re-implement things is the classic case of Netscape 6. So Joel on Software wrote one of the fundamental essays about software programming, and I have a link for it, and I'll put a link to this essay in the description down below. You should give it a read. But basically what he's saying here is that when Netscape went from 5 to 6, they decided to completely redo Netscape from scratch. And what happened here was that because they decided to do Netscape from scratch, Microsoft Internet Explorer came in and basically ate their lunch while they were taking an extremely long time to redo their application. So you don't want to fall into that problem. So you want to build on the shoulders of giants. So, but let's move on. Let's assume that you've got a good reason to want to make a SAL, a single application Linux. What are the components of that? Well, if you're going to make an ISO, you're going to make a CD-ROM or an application that runs off of a USB stick. There are three components that you have. You have syslinux, you have the kernel, and you have initramfs. All of these are bundled into the ISO. Syslinux is comprised of a configuration file called isolinux.cfg and two binaries called isolinux.bin and ldconfig.c32. Alternatively, or in addition, you can create a boot.txt, which just does a nice little flash on the screen telling people what they're booting into. The next component of the ISO is your kernel. And it's the BZ image that you traditionally do when you compile your own kernel. And while you're at it, let's go compile up a kernel because this takes a few minutes. So let's get that up and running. So how do you compile your own kernel for this project? Well, we're going to start off with a make Mr. Proper so that we've got a clean source directory. And then we are going to make x86 defconfig. And we will remove some features that we know that we don't want by menu config. And I am going to take out the virtualization ability and the ability to load kernel modules. And that's it. You can take out more if you want, depending on your need for single application Linux. So for example, you might want to remove all networking support. And then I'm going to start compiling it up and we'll go back to the presentation. The last component of your ISO is going to be an initramfs. And the initramfs is comprised of your application, which has been statically compiled. So let's get into the demo. And while our kernel is compiling, let's take a look at this make file that I've got, which does all of the work for us, with the exception of creating the kernel. So we are going to make ourselves a file called sal.iso, and it will be comprised of syslinux, and this is just a stand-in for the entire syslinux, and the initramfs. So how do we get this syslinux isolinux.bin? Well, we're just going to download it via the syslinux repo. So we're just going to download it and copy it into our resources file, and we will copy it into an isolinux directory when we make the sal.iso. And the other part is the initramfs. So how do we do the initramfs? The way in which we do an initramfs is we make a ramfs directory, we copy in our application to that directory, and we rename it to the file name called init. And then we use cpio and then gzip to create the initramfs. So let's give that a start here. Let's do a make clean all, just to make sure that we're all good, and make our app. So yeah, and while the app is being created, let's go through what the app does. So the app is just a simple Rust program. It's a simple file, a simple single file here. And what it's doing is it's going to use a framework called Rocket to start up a little web server that will simply serve us the website with Hello World on it. Also, it's going to have a loop which is going to ask us to input some commands. And if we type hello there, it's going to reply to us General Kenobi. But otherwise, it's just going to repeat what we typed in. So the application is just about complete. All right, now I'm going to generate the initramfs. So I'm going to do that by doing a make ramfs. And you can, that was pretty fast, it's all done. And you can see that our kernel is finished as well. So the last thing I'm going to do is make the sal ISO. So that's going to copy in our initramfs, the items from syslinux and the kernel, and then it's going to bundle them all up into sal ISO using make ISO-fs. So let's do that right now by make sal.iso. So it's grabbing syslinux. And it's all done. So let's give that a run inside of a virtual machine. So I'm going to do that by using my QEMU run scripts and saying that it's going to be passed a CD-ROM of sal.iso, and I'm going to forward port 8888 to port 8000 here. That runs. And we're up and running already. Now, ignore these errors that you see on the screen. Let's just pretend that this is all that came up. So if we type hello there, we get General Kenobi. And if we type quit, it stops it halts the machine. So that's great and all, but the thing is, we're supposed to be running a web server here. And these errors are actually the web server saying it couldn't start up. So this is where I'm getting back to the problem of needing to stand on the shoulders of giants. Because we only have a single application here, we haven't initialized the networking. We haven't done an ifconfig eth0 up. We haven't initiated DHCP. We don't have an IP address. Because we don't have an IP address, our web server can't start properly. So we need to solve that somehow. So one way we could solve that is to re-implement all that stuff ourselves. But like I was saying before, that's a bad idea. That work has already been done. So what we can do is, instead of running a single application Linux, we can run a 2 application Linux. So the 2 applications will be our web server and an application called BusyBox. Now, BusyBox is a very interesting application in that it does a whole lot of things for us. But what we want it to do for us is to bring up our network interfaces and to get us a DHCP client. And in order to do that, I'm going to do a make clean here so that we don't have that ISO anymore. And what we're going to do, instead of just packing up our initramfs with only our app, we're going to package up initramfs with BusyBox, an initialization script, and our app. So we should get BusyBox by make get BusyBox. And so we've got BusyBox now. And then let's take a look at the init script that we're going to run. So this init script is going to initialize BusyBox, and this install flag basically expands BusyBox into having into understanding what you mean by if you type mount, or so when you call mount here, that's actually saying, hey, BusyBox, run your mount function. So yeah, it's going to expand BusyBox to give us all of these core utilities that we will want. and then it's going to write a few files to let BusyBox UDHCPC to understand how to give us a DHCP client. And then finally, it's going to bring our network interface up, and then it's going to run our app. So let's make that now. Make busy. And it's already got everything that we need here because everything was compiled up. And now let's give our ISO a run again. But this time it's with BusyBox on it. So it takes a little bit longer to start, but you can see that we've got a few more prints here than before. You can see that UDHCPC has said that it has a lease at 10.0.2.15. And one of the things that I do inside of my run script is that I'm port forwarding port 8888 on my host machine to port 8000 on my virtual machine. So this means that I should be able to now go to my local host, port 8888, and that will be forward to my virtual machine running this 2 application Linux, running my web server. So let's do that, and you can see that we've got the hello world. So that's pretty cool. Again, we can just quit to stop it. And one of the interesting things about this sal.iso is that it's only 12 megabytes large. So if you were able to go into this single application Linux and have a shell, in fact, let's actually do that to show that to you. So I'm going to edit my init script to, instead of running my application, we're just going to run a BusyBox shell. So let me remake the ISO and rerun it. So we're now in the shell, and you can see that we've got ls here, ls.la. We've got a bin, a dev. If we go into dev, you can see that we've got a bunch of devices on the machine. We have, if I go into bin, you will see all of these applications here. So if I cat on vi, oh, okay. I guess the way that BusyBox worked here is, let me restart this. Looks that BusyBox copied itself. You can configure BusyBox to copy itself, or to make symlinks to itself, or to create scripts that call its functions. Let's get back into it. So there's I wonder if we've got grep here to grep away. No. So all of these things in braces here are parts of the kernel. Let's do less. Do we have less? Yeah, so you can see that we have PID1 as BusyBox shell. And then all of these other processes are actually part of the kernel here. And then we have our UDHCP that's giving us an IP address, PS, which is what we just ran, and less, which is what we just ran. So now I'm going to run our app. So now we've got 3 applications here running. We've got BusyBox, we've got UDHCPC, and we've got our application. And in the case of this configuration, where we're not running the shell, we're just running our app, we've only got 2 applications running, UDHCP and our app. So one more thing that I'd like to show before we go here is that this ISO, the sal.iso, can run on hardware. So I'm going to make sure that I've got the correct starting application here, or moving into our application at boot after we've started up our network. So let's make busy just to make sure that we've got everything right. And I am going to take a USB stick and I am going to load it with that sal.iso. So let's see what happened here. I plugged it into SDC. So let's sudo dd and I am going to plug it into this old ThinkPad here. I think it's about 5 years old, maybe 6. And select booting from the USB stick. And I need to find out the IP address for this machine. So I'm going to use nmap to do that. So I'm going to nmap for my network on port 8000. And I'm going to grep for open and put a flag for everything before open, 4 lines before open. Let me do that again because I didn't get it on camera. So I'm going to nmap my network on port 8000, grep for open, and get the 4 lines before that open word. And we can see here that it's on network on IP address 192.168.0.140. So I'm going to go on that website, and you can see that we've got this hello world. Let me reopen and go to 192.168.140,000. And there we are. So yeah, I hope you have learned something about Linux. I hope that this has given you some ideas about how you can keep going with your Linux discovery journey. Maybe it's given you ideas about how to utilize a Raspberry Pi to do a single application Linux with it. So yeah, have a good day or a good evening or a good morning.